expansion. Okay, and we saw, for example, that A would be the dynamic, so it's like df dx evaluated at a fixed point, and so on. A represents the dynamics. B here is the coupling between the input and the dynamics. Y is also a linear relation, is related to the state and the input as well. The C is the output coupling. It says how you go from the state to what you measure. And D, which we usually won't have, is this feed through, which is a little bit like the Ohm's law relation we were talking about. Okay, and we asked a little bit about when can an input U, for example, a single input, control a system that has an n-dimensional state vector. And since U is only one component and the state has n components, you might think there's a problem. But remember, U is a function of time, and so it's what you can do over time that counts. And so what we saw was that there was actually a test that one can make from the matrices A and B. You construct this matrix here. Each of these is a column. And if this is full rank, if it's invertible, then we showed that an input basically reaches out and spans all of the n-dimensional space of the state, and so you can then control anything. I sent around some notes last night, and I think they got posted this morning. So on the website, you can see a written version of this. I'm sorry, it's in kind of my bad handwriting, but it does have the advantage that sometimes I'm skipping over steps, and so there are a lot of steps that are done. Okay, so if the system is controllable, then as I mentioned, and the proof's in the notes, that if you put a feedback like this, you make the input proportional to the system state deviation from where you want to be. So here, everything is in the context of just wanting to bring back x to 0, which is some point in the state space. So if you take an input of this form, where k is, if U is a single input, k would be like a row vector, and this would be like a row vector on a column vector. If U were multiple, this would be a matrix, and so forth. Anyway, if it's controllable, then you can take an input of this form, and if you stick it into the equation, then you get a reduced or a closed loop dynamics, where the input, the feedback has been sort of absorbed into the system and creates a new dynamical matrix A prime. And the claim, and again, it's backed up by stuff in the notes, is that if the system is controllable, then you can give A prime essentially any properties that you want. And specifically, remember the solution we got is something of the form e to the at. And so this, if A were a diagonal matrix, this would be, for example, e to the lambda 1t, e to the lambda 2t, and so on, e to the lambda nt. So if it turned out that in your coordinates A was a diagonal matrix, that would correspond to having n separate systems, each one of which would have a time evolution e to the lambda 1t, which I guess in this sign convention would have to be negative in order to be stable. And so you'd have n of these, and what this is saying is that we can choose the elements of k to make, for example, these values of lambda be anything we want. Okay, so this is where we got to last time, and it leaves open a big question, which is, okay, this is great that you can, choose these elements and make these what you want, but the question is, how should you choose them? And that's what I wanted to talk about today. The other question that we didn't answer at all is what happens if you want to think about more than linear systems, and so we'll also talk about that. Okay, but before I start, were there any questions from yesterday? Yeah.
if it's possible to think in a question about how easy is to control a system. There are measures of that.
Yes, absolutely. Okay, the precise answer, it's also one of the things that was skipped over in the notes, is you can form, let's see, so if you form EVT, and then you take the transpose. Okay, so this quantity, this would be like in the single input, single output, for example, this would be the impulse response, and then this is like the adjoint of it. And so this forms another matrix. So we can call this, I forget what I call it, P or something. It's called the control Gramian. And so this, sorry, and we integrate, let's say, in the simplest case, let's just integrate overall time. So this gives, you can show that this gives a measure of how much effort, let's say energy loosely, it doesn't always correspond exactly to energy, but let's just say how much energy does it take to perform a control. So looking at the size of the elements of this matrix and its eigenvalues, for example, sort of says like how much energy does it take to control it in a certain way. And as I think I did say yesterday, matrices such as this tend to have a condition number, the ratio of largest to smallest eigenvalues that grows exponentially with the size of the system. So there will be lots of things that you might want to control that would take huge amounts of energy to do. And so in some practical sense, they wouldn't be controllable. So there's you're absolutely right, there's kind of a nuance. I mean, we were doing the very crudest thing of like possible, impossible, but then you can start to ask, is it easy, is it hard? And that's sort of the starting point there.
Okay, thank you.
Okay, good. So let's see. So now I want to, maybe I'll just, there's a little bit of this in the notes too. Okay, so I want to introduce something, a concept called optimal control. So this will give us a systematic way of, for example, choosing these elements or constructing a control. And I should say before I get started on it, that there are all sorts of heuristic ways that one could try that are not as systematic. So you could, for example, take the dynamical matrix A, and one rule of thumb would be if, so this is just a prequel. So if we had A and we characterized it by its eigenvalues, then all the eigenvalues that we want everything, if it's stable, to be in the left-hand plane, but you might have unstable eigenvalues here. So that would represent a mode that would grow exponentially. So if you had feedback, you would want to stabilize that and make that go away. You could also have, for example, a bunch of stable modes, and some of those could be, for example, oscillating. Because we're dealing with real systems, anytime you have a complex eigenvalue, you have its complex conjugate, so they come in pairs. So this is the im lambda, this is real lambda. And a rule of thumb, for example, would be take any unstable eigenvalues and use your power in here to somehow put them over here. But then, for example, you might have modes that are stable but very slowly decaying, and maybe that's not so good. So then you could say, well, if, for example, if the system is not decaying quickly enough for you, then take the slowest modes and push them down a little bit. But what you find is that there's nothing to be gained from sort of taking these other modes in here and pushing them more. That just costs you control effort and won't really get you anything useful. So sort of taking, as few of these, modifying as few of these eigenvalues as little as possible would be one rule of thumb. And often, that's not so bad. But I wanted to give another way of doing this, which is more, well, which is different. Okay. So let me just, so the idea is going to be roughly that we introduce a scalar function that quantifies how good a control is. And I'll follow theory, but sort of like how costly a control is. So the control that has the lowest value of this will be sort of best. And we'll try to see what this means. But let me just introduce this by a very simple explicit example, and then we'll try to generalize. So I'll call this function j, and it will depend on the control that I exert from now, let's say indefinitely to the future. It might just be a finite time, but let's do it indefinitely for the future. And this will be my notation for u of t with 0 is less than t is less than infinite. So just the trajectory of u. And it also depends on the initial value of the state, which is just a vector. And in this case, I'm going to do a one-dimensional example, so this is actually a scalar, and this is just a scalar trajectory. And so let's just look at something that's of the form 0 to infinity L of x and u, and I'm going to define this function here to be a half q x squared of t plus r u squared of t. Okay, and q and r are just positive numbers here. And so what this is saying is that I have some dynamical system, which I haven't even told you what the dynamics are yet. And my goal, in some sense, if you look at this, will be to, so you're penalized, you get a larger value of j when x is different from 0. Okay, so this says it wants the control to keep the system as close to 0 as it can. But just to make it interesting, it also wants to make u as small as possible. So u is the amount of control that you're doing. So you have some system, and in this case, it'll just be x dot minus ax plus u with x of 0 equal to x naught. And let's just say a is greater than 0. So this is a stable system, but it's starting out, right, so this is a system that would start off at some x and naturally will tend to decay. All right. However, if we choose, for example, u is equal to minus kx, then just repeating, doing this exercise here means that x dot is minus ax minus kx, so it's minus a plus kx. So you can see that this system here, if we didn't have u, this one here will decay at e to the negative at, and so that's okay. But we have the option of adding in, for example, some feedback with gain k, in which case this will decay down here, where this is now e to the negative a plus kt. So this will make it decay faster and go back to 0 faster. And so we're asking, how do I choose k such that I minimize this function that I've defined? So the idea is that there's some trade-off. You want the system to do what you want the system to do something, but you also have to exert some control. And if that control comes with a cost, then you want to balance how costly is your control with how good are the results. Okay? So in this particular case, it's really easy to do this explicitly. So if we have dynamics like this, then x of t is x naught e negative a plus k t, and u is just minus kx. So we know what x of t is, we know what u of t is, and so we can just stick it into this integral and do the integral or ask Mathematica to help. And you get 1 plus k squared over okay, so that's just putting in this and this into here and just doing an integral. Okay, and so you get something. So then in optimal control, you would say, all right, we want to pick the value of k that minimizes j here. So k is a free parameter, right? That's what we're trying to choose. And now we have a way of choosing it, so we're trying to minimize j. So we can take dj dk equal to 0. And when you do that, you get a I'll spare you the algebra, but 0, so that k star, oops, okay, yeah, thanks. Okay, so you take d by dk of this and set it equal to 0. That gives you an equation for k, and then you can actually solve this equation explicitly. We would have to, if we want to keep k positive, we would take the just the positive root of the quadratic. And so then this looks like something like, for different values of k, something like this. This is for r equals 10, 1, and 0.1, and this is k, and this is j, and so we're finding kind of k star here for a value. So this is for, so one thing you can see immediately is that since this is a scalar and this is a scalar, and we're just looking for minima, we can always pull out a constant or scale, let's say scale j by q. So we just, I'll set q equal to 1, or just look at the ratio of r over q. Okay, so this is r, or r over q equals 10, 1, and 0.1. And so you just get different values, and you can take limits, and I think I'll skip some of the algebra, but you can take limits for r being very small or large. When r is very small, then it's saying that you want to minimize, you want to make x small without caring how
Could I ask something?
Sure.
Why q doesn't appear in the expression of j?
Sorry, so this is for q equals 1.
Okay, thank you.
So it doesn't, so because it's proportional to both of them, you can just scale one of them away. Okay, so yeah, so if we were to plot this versus r, you would get something like log r would be something like r to the -1/2 or -1. So for very large r, then it's saying you just want to do nothing and let it decay naturally. If r is very cheap, you want to use a huge amount of gain and a very large value of k. Okay, so I chose this example because it's one that we can do every step explicitly. You might say there's not much point in the exercise that we just did, in that we had a system, we wanted to try to stabilize it in the way that I was talking about here, and I said, well, you have to choose k. All right, and we come up here and we realize that our choice of K is going to be just related to how we choose R. So all we've done in some sense is exchange choosing K for choosing R. Okay, so in a setting like this is so simple that there wouldn't really be much point. You might say that, well, again, maybe I have more intuition about what R means than what K means. Here I'm not so sure. I mean, K just makes it go faster, and so it's pretty obvious. But the idea will be that when we go to more complicated problems, we have the same structure, and hopefully we'll have some insight into how to choose these quantities. And so we can sort of exchange a kind of abstract, because remember, for example, if X is an n-dimensional state, for example, even like a harmonic oscillator would have position and velocity, so you'd have two elements, but it could be much more complicated. Then you have to choose n gains, and if you then have m inputs, it would have to be n times m things to choose. And so it's good to have something where you have some more intuition. The other thing to point out is that when we say optimal in optimal control, that suggests sort of like it's the best, but it's always with respect to some kind of criterion. So, we had to choose in this particular case the form of this quantity and the values of Q and R. And if we make silly choices of these values or these quantities, then we'll get a silly control. So when somebody says they're doing the best, you have to always ask like the best with respect to what criterion. Okay. Okay, so I want to do this in more generally, but are there any questions before I launch into that? Yeah.
You said you were going to introduce a figure of merit for the control cost. Is that what J measures?
Well, here, the way I've defined it, J is some linear combination of the sort of quality of control and the cost of control. So depending on how you weight these numbers, you can kick, I mean, if R is going to infinity, then you don't care about the cost of control. The control is so costly that you don't want to do anything. If R is going to 0, then it's saying all you care about is the results, and you don't care how costly it was to get there. But here, this allows us to sort of balance those costs.
Okay, thank you.
Yeah. Okay. Let's see. I think I'll go in here, I guess. Oops. Okay, so in the general setting, I'll have this J, and I'm going to let it be a function of two things, actually. So I'll put in something that depends on the state of the system at some final time. So I'm going to be thinking the general setting will be, I start in some initial state, and I end up in some final state, and this transition takes a time tau. Okay, so this will be something that is a function, it just depends on where you end up. And then it will also have, so this is a tau, a function like the one we were looking at before, which integrates over the time from when you start to when you end. Before this was infinity, but now we'll put it as a finite time. Okay, and so this will allow us to say, by putting in various coefficients, we can say, how much do we care about what we might call the running cost? So this is costs that you incur while you're doing some protocol. And how much do you care about the result? Okay. So this J is going to be, again, a function of U on the trajectory there. So we would say technically it's a function now and of U, the trajectory U, but a function of the initial state X naught. And we could let tau go to infinity if we wanted, and then we would just drop the final condition since there isn't any final condition in sight. Also, just in sort of general kinds of things, this could be expressed as a soft constraint, in which case you want, for example, X to end up near some desired state at the end, and you put in some cost when it doesn't match that. Or we could also put in a boundary condition and just say, in some sense, this would we'll put in infinite costs for deviations, and in effect, we'll force the system to be at a particular state. So we can do all of those kinds of variations. Okay. So this running cost, we had it as a quadratic. More generally, it might not be a quadratic. So for example, if we look at this as a function of X, then it might, before we were looking at something like this, but in general, maybe, you might argue it should look something like this line here, which says that, you want, let's say, X to be 0 as an example. For small deviations away, you might ask for a quadratic cost, but for large deviations, you might say, well, once it's far away, it's just bad, and there's some, bad cost that we will cap at some amount. But we can also just look sort of for small deviations and use it as quadratic. So in the formalism that we'll do, the idea is that we now have an expression of our costs, but we have to sort of impose the dynamics. And so the idea is that we're going to impose dynamics of the form that we started with. So we're back to the nonlinear case for the moment. And we would like to impose these as a constraint. That is to say, here, we're just looking for costs where X and U could be arbitrarily related, but we know they have to be related through this dynamical equation here. And so the idea is to use constrained Lagrange multipliers to do a constrained optimization. So what this means is that I'll call it maybe J prime, so it's an augmented cost, and it's going to be phi of X of tau plus our integral over the running cost plus an integral over a Lagrange multiplier, and I'll write it like this. So this constraint has to be enforced at every time. So all of these X's and U's are functions of time. And so this Lagrange multiplier also has to be a function of time. This equation is an n-dimensional equation, right? There's one for every component of the X vector. And so this Lagrange multiplier then has to be, we have to have n of them, and they should be a vector so that they are applied to each component. Okay, so I'm sort of hoping that Lagrange multipliers are stuff that people have seen. So again, you put in a Lagrange multiplier to turn, and with a constraint, so that you can turn a constrained optimization into an unconstrained one with extra variables. And so then the idea is that we'll look and do a calculus of variations and set this equal to 0. And we have to do variations not only in X and in U, but also in lambda. Okay, and so again, this is the Lagrange multiplier trick that turns the constrained optimization into an unconstrained one with extra variables. Okay, this lambda has various names. It's sometimes called the adjoint, sometimes called the costate. And I think I'll usually just call it the adjoint vector. But because it's an n-dimensional vector, it's sort of living, in terms of the equations, with the same status as our original equations x of t, for x of t, the internal state. So x of t is an evolving n-dimensional vector. Lambda of t is also an evolving n-dimensional vector. So they both are relevant and have to be determined. Okay. So so if we had a bit more time, I would go through the full expansion for calculus of variations. But again, I'm hoping that this is something, if you've taken classical mechanics and done Lagrangian mechanics, that you've seen in a simpler case. And it's really just the same kind of stuff and the same kind of tricks. What you get are called Euler-Lagrange equations. And what they are is, so the first one of them will be actually just the dynamics that you sort of retrieve. So this is also characteristic of problems that you solve by Lagrange multipliers, that the constraint is one of the equations. The second equation, so this is an equation for x, so this is what we would expect. But we also get an equation for dynamics of the adjoint. And so this obeys minus dxf transpose lambda minus dxl transpose, and then there's also a boundary condition that lambda of tau is dx phi evaluated at tau transpose. And then we also have one more equation, 0 is equal to uf transpose lambda plus ul transpose. Okay, so so this is an equation that has an initial condition, so it goes forward from 0 to tau. This equation here has a final condition at tau on lambda, so it being a differential equation has to go backwards from tau to 0. And this is just, in some sense, there's no time derivative here. This is just a static equation which is holding at time t. Okay, so we have three sets of equations to worry about. In a couple minutes, we'll clean them up a little bit to look a little nicer, but I wanted to sort of start with just what you would get directly by doing the variational calculus here. Okay, so just like when we were looking at j as a function of k, and we had relationships like this, and we found them by looking at dj dk equals 0. I didn't show that what we got was actually a minimum of the cost. You could look at a second derivative to convince yourself of that. But you remember that we could have had this, we could have had some point of inflection. So this is a necessary but not sufficient condition in this case. And similarly, when we take a variation, look at first order functional variations, we're getting a necessary but not a sufficient condition for a minimum. Okay, so that's always something to worry about. The second thing is, can we sort of interpret a little bit, and this will come gradually, but let me just sort of sketch where we're going. If, for example, we were to, so this f here depends on u, and u and lambda in this equation get related. Okay, so u and lambda are not independent. But if we just pretended that there was no lambda dependence in this. This would just be lambda dot is minus, let's say, some constant related to lambda. So this would just be a linear equation driven by this term and evolving backwards in time. And again, the minus sign here is sort of the confirmation that the sort of relevant evolution of lambda is back in time. And it represents, I'll try to convince you as we go along, a kind of planning variable, you might call it, that it's sort of telling, because lambda and you are coupled, it will be telling, lambda will be telling you what to do in the future, what to do now so that the future comes out the way you want it to come out. We'll see, this will make more sense, I think, in a few moments. And then the final, just sort of mathematical note is that if we, we've talked about x going one direction of time, lambda another direction of time, but in some sense we have to solve for a coupled set of equations involving x and lambda and even u, and we can think of them as a boundary value problem. And this is the thing that gives the optimal control problem kind of a different flavor from classical mechanics. So classical mechanics, we just have something like this, or classical dynamical systems. We would say, okay, we know the system now, we know what we want to do with it, or we do something with it that we know about, and then we just find out how it evolves in the future. So you have a pendulum and you kick it, and you just see what it does afterwards. But this equation is really for the combined set of variables, and they're constrained at what you want what the system is now, and what you want it to be in the future, where I'm thinking now of the system as having both x and lambda and u all sort of put together. Okay, so it turns an initial value problem into a boundary value problem. Okay, so let's go back to the one-dimensional equation, which I just erased, but let's remind ourselves that it's a half x squared. So I'll just take q and r equal 1, and so we have, and I'll take everything equal 1, so the negative x. So this is sort of a particular case of what we had before, and we'll do exactly what we did before, but now let's take an initial condition, and let's say at time tau we want to impose a final condition. So we'll say x of tau is equal to x tau. So this is, so unlike before where we just said, we're going off to infinity, here we'll say at some finite time we want it to have some specific value. It might be 0, it might be something else. And so then the Euler-Lagrange equations, if you just stick the L for this and stick this into these equations, you'll get x dot is minus x plus u, because we have to reproduce that. Then we get lambda dot is plus lambda minus x. So this is the evolution kind of, see, notice that this will be stable. Lambda dot equals lambda has a solution of e to the t. E to the t, it's unstable if you're going forward in time, but remember it's stable if you're going backwards in time. Okay, and then it's driven by this x term here. And then this third relation turns out to just be u equals minus lambda. Okay, so they're fairly trivially related. And if you, so this now you can think of as, once we put in for this, it's basically a second order equation with a condition at the beginning and a condition at the end. Okay, and so then you can solve for it. And if we put this as, like, if we start at 0 and go to 1, for example, then this is time, then we'll have some x, this is 1 and 0. So this will be x of t. And then lambda will do sort of essentially just the opposite. It'll be diverging in the other direction. And we can sort of think of lambda here as, lambda is related to u. And so, actually, maybe I'm plotting, I think I might already be plotting, no, this is right. Lambda is negative, so u is positive. And so this lambda is in some sense telling u to go positive. It's sort of like telling the system, hey, wake up. So the optimal thing to do here with with our balance of a coefficient of 1 here and 1 here is not to do very much in the first amount, and then towards the end or somewhere in the middle, sort of wake up and start to exercise the control. And if we were to put in R here, for example, then if we had a very large value of R, that would make it tend to wait longer before it does its thing, and if a smaller one, then it might start earlier. And so, yeah, so this formalism then, can generalize the kinds of problems that we're doing. But what's nice about this formalism so far is that it's not a linear formalism. So this is a linear example, but we could just as easily, or almost as easily, do a nonlinear example. So if we go back to our example of the pendulum that we talked about. So let's think about the task of swinging up a pendulum. So we have theta double dot plus sine theta is some torque that we're applying. And let's we'll have, in this case again, initial conditions that are it starts it starts hanging down. So this is theta equals 0. So theta and theta dot are equal to 0. So and then we want to go in some time tau to, let's say, an upright position like that. And this will be pi 0. So we have x, which is, so the vector x is theta and theta dot. And so we wanted to go from this point to this point, which corresponds to going from down to up, down in stationary to up in stationary, okay, in some time tau. And so in this case, it's of this form, except here, this is going to be just expressed as a boundary condition, a final condition, rather than a soft one. But we could have a soft one as well. And so then we have to specify the j. And for this example, let me just have a j of the form. So I'll ignore, this is only counting the cost of applying the control. And so what we're saying is that at the beginning, I'm down here. At the end, I want to be up here. And in the middle, I don't care what the system is doing. So I don't care what trajectory that it does, as long as it makes it up to here at the end. But what I do care about is how much energy or how much effort I have to put into moving, to torquing it so that it goes. And so I'm trying to minimize the amount of effort while still balancing it at the end. Okay. So actually, we really have everything here to do this problem numerically, which is pretty much the only way you can do it. We have, this can be rewritten in terms of, I think we did this already, x dot equals f of x. So we take this and make it, we get our f. We have our L here is just a half u squared. There's no phi. So this would just be, well, this is actually unspecified. Since we don't have a phi, this is unspecified, but we have x that's being specified in 2 places. Lambda is not being specified anywhere, but if you think about the number of boundary conditions that you would require for, so that we have 2 components for x, 2 components for lambda, so we need 4 conditions, and so we're applying them. Here are 2 and here are 2, so you don't need any conditions on lambda. If we had sort of had a soft constraint saying maybe we want to get near the top, but don't have to exactly get to the top, then we would put then the conditions would end up being on lambda. Okay, and so you can do this, and so the solutions look typically something like, well, let's see. And oh, actually, let me do it the other way, just to, because I use colors in my notes, so I actually used a red color in the notes. Oh, no, no. Sorry, I had that right. Sorry. I think I'm going colorblind. And then, let's see if I get this right. Something like this. So this is u of t, and this is theta of t. This is pi. Okay. Okay. I'm not going to use it so much red. So. So anyway, so what this corresponds to is giving a torque that's kind of going back and forth like this, and eventually, so the pendulum then is swinging, and then goes like that. And if I were more professional, maybe I'd have a movie, but you can get the idea. Okay. So this is and this is for one particular tau. And what's nice is that you can vary tau, the amount of time, and you'll see that the u that you need is sort of bigger and bigger. And also what happens is that there's a natural time scale, of course, which is the period of the pendulum. And so if tau is very large compared to u, then the optimal thing in terms of putting the least effort in. Remember, there's no friction here. Okay, so we could put friction in, but there isn't in the way I did it. So basically, it would be swinging, and with every swing, you would just put a little bit of torque to help it along, so that it's swinging more and more and more, and that's advantageous because since we're penalizing u squared, which we want to do because a torque, in this direction and a torque in this direction should be equally costly. So symmetry says this should go as u squared. That means that sort of taking smaller value, keeping your values of u very small over a long time is better than a giant violent torque right at the beginning. But if you only allow a small amount, then the giant violent torque is what you want to do. Okay, so you actually get a pretty complex set of solutions that come out of this. Okay, questions about this? Okay. So this is a formalism that starts with something, this L you could think of as kind of a Lagrangian if we're going back to classical mechanics. And so one thing that you might wonder about, well, whenever you do Lagrangian mechanics, Hamiltonian mechanics is not far behind. And so the question is like, is there a sort of a Hamiltonian version of this? And the answer is yes, and it has some nice features. So you remember that maybe, okay, let me do it over here. Okay, well, we have this set up here pretty much. So if this were classical mechanics, the Lagrangian would be kinetic minus potential energy, and then this, so that's the Lagrangian. And then we would define generalized momenta, P defined as dl dq dot. And then we would do a Legendre transformation. Defining H is P q dot minus L. And then we would get Hamilton's equations, which are q dot is dp h transpose p dot is minus q dh transpose. Yeah, I mean, the transposes are coming just because I'm trying to, I suppose it's more engineering notation or not, where gradients when we take gradients here, we'll get a row vector. So if we want this to be a column vector, then we should take the transpose and make the gradient a row vector again, and so forth. Okay, but up to things like that, these are just the familiar Hamilton's equations. And so here, we can do something similar. So we have L plus lambda T x dot, or L plus lambda T F. So this looks kind of like the classical mechanics, except that by convention, at least in the control literature, this is introduced with a plus sign. So if we were doing this transformation exactly, we would do it with a minus sign. But apart from this one sign, it's basically the same. And so then you can go through and introduce this and either directly derive through stationary action the Hamilton's equations, or you can take these equations here and just rewrite them in terms of the Hamiltonian, and they're equivalent. And so what you get then is x dot. So if we define our h this way, then x dot is the lambda h transpose, which is just f. Okay, so that's our original equations of motion. Lambda dot is minus dx dh transpose for the adjoint, and then the third equation is just du h equals 0. Okay, so these equations here are just the same as these equations, but expressed in terms of this quote-unquote Hamiltonian, which is related like this to the Lagrangian, to the running cost. Okay, so if nothing else, this is a lot easier. This is a lot easier to remember than this, but they're really equivalent. One thing I would point out, and actually this is something where I've yet to, there probably is an answer, but I've yet to encounter it, which is that in classical mechanics, we can define our Lagrangian and generalize momentum and so forth, and come up with Hamilton's equations for systems without dissipation. So they have to be closed systems. But in this formulation, this x dot equals f could be any kind of an equation. And in particular, it could be an equation that has dissipation and inertia in it. So it's at least interesting, but probably more meaningful, that even though we're dealing with dynamical systems that are dissipative, have both inertia and are dissipative, we're still getting something that has the structure of Hamiltonian equations. So I'll leave that as a thought to percolate. Anyway, okay, so having formulated these equations in this way or this way, there's one case which you can immediately guess what it is that can always be solved, and that's the linear case of linear dynamics. So I want to go back to the linear dynamical system and then look at what these equations say. Okay, so it's linear dynamics and also quadratic costs. So the J is going to be, and I'll go back to, I'll ignore the n costs, but say 0 to tau dt of, so my L will be a half okay, so this is, before we had a half qx squared, but now we're thinking about a general case where x is n-dimensional, so this could be an n by n matrix, and we might have more than one input, so this would also be a matrix if that were true. These are symmetric matrices, and we'll need to have them R be positive definite and Q be semi-definite, positive semi-definite. Okay. We also have x dot is ax plus b u. We're not dealing with observation, so we're sort of assuming that we always have access to the full state vector if we want to use feedback and so forth. And then our h, if we then put in, is just a half xt qx plus ut ru plus lambda ax plus bu. Okay, so right away we have our Hamiltonian, and so we can just put in these equations here. And so what they give are, of course, they give x dot equals ax plus bu, and then they give lambda dot is minus at lambda minus qx. So we can see again, this is the adjoint dynamics. The a has come in through its transpose, and then there's a change of there's a minus sign for essentially going backwards in time. And then the final equation is u is negative r inverse b transpose lambda. So this is again a linear relationship between lambda and u. Now lambda and u can have different dimensions. So these are vector quantities and so forth. They're vector and matrix quantities. Okay. So then if we want to solve this, the ansatz that we can make, or the substitution that we can make, is the first thing is try something that is of the form minus kx. So k, or sorry, I'm skipping a step here. Sorry, the way we'll do the ansatz is to write lambda equals s of t times x of t. So this says that so remember lambda and x are both n-dimensional vectors. Okay, so this means that the S is an n by n matrix. This is just a ansatz. In other words, we're just guessing that this might work, and this only works basically for a linear case. So in general, if you try this, it won't help. But for the linear case, it does. Then when we put in lambda equals s times x here, then we have something of this form. Okay, so then this is actually just, well, yeah, it is a definition of k. Okay, so then the next step would be, and I'll abbreviate this, but you put in for the equation of lambda dot here, but since lambda is s times x, this is also an equation for s. And so what we really want is the equation for s, and so that is s dot is minus q s. So what I've done here is put lambda equals s times x, and then you'll get x everywhere. So I factored that out, and this is just the equation that's left from the prefactor. Okay, so this is an equation. It's a little, in some sense, it's a little bit of a nasty equation in the sense that it's a quadratic equation. So here's an s squared. So it's a quadratic equation for this matrix S. So it's a nonlinear ordinary differential equation for a symmetric matrix S. Yeah, it's called the Riccati equation. Oh, I always forget how to spell Riccati. I think it's two C's and one T. Yeah, okay. I always get messed up by that. Okay. How about, does that look good? Okay. Yeah, it's called a Riccati equation, differential Riccati equation. and so we can, for example, go back to our original 1D control problem that we had, and let's see, yeah, I think now I can erase this part. So in this 1D, in the 1D control problem, remember it was x dot equals negative ax plus u, and j was a half, or L was plus a half of u squared. And so then from here, so k is going to be R inverse B transpose times S. And so we'll have K is R inverse B transpose S. So that's just going to be S over R in the scalar case. A is minus A, B and Q are 1. And so then this Riccati equation turns out to be S dot is minus 1 plus 2 S plus S squared over R. So now it's just a differential equation for a scalar, but it's still a nonlinear one. In case you're looking at very long protocols the way that we did before, you could solve for steady state, and so then you would just get so steady state would be S dot equals 0, so that's a quadratic, and then this gives you S equals minus A R plus or minus A squared R squared R. And if you divide, so K is S over R, so if we divide by R, then you'll see that we get back just what we had before. But now in this formulation, we could also say that we want a protocol that stops at a finite time tau. And then we would impose a condition. And the condition that we want to impose is that the gain or the S at time tau is equal to 0. And intuitively, the reason, one can derive it, but intuitively the reason is that when you activate U in this simple example, you're paying an immediate cost because, let's say you're trying to get it to accelerate more towards the thing, but you only get the full benefit when you integrate later. And so right at the end of the protocol, it's basically never worth it to put on any gain or to do any control, because the benefits of those control will come after. Like the system has a finite response time, so whatever benefit you get, you pay the cost now, but you get the benefit later. And so at the end, you don't want to do that. And so that corresponds to just putting a, so then the gain that you would get would be, if this were the time tau of the protocol, it would start out 0, and then it would go to a steady state value, which is just K equals S over R. Okay, so it's just what we, so if tau is long enough, then it's just the case that we had before. But now we can put in a finite time and see how we would sort of turn off the feedback as we get towards the end of the protocol, and the gains become less important. Is that okay? So this has given us a kind of systematic way of looking at a wide variety of controls and figuring out what the control is that's quote unquote best. I wanted to go back to this idea a bit about planning. So actually, when did I start? Like, how much time do I have? Any thoughts here? I mean, we started definitely late, so sorry? 15? Okay, ish. Okay, okay, so there's a bunch of things I won't quite get a chance to talk to, but let me talk about one thing. So I want to think about a discrete optimization problem, which if turned into a continuum limit, and we won't have time to really do this, honestly, will basically be the same problem. And so this is, imagine that we start at some location, and every day we make a journey, and we can go to this city or that city, and then on the next day we can go to that city, this city, but we want to get to the end town. So I'm sorry, my Colombian geography is totally inadequate to giving an example, but we'll keep it abstract. So every day you have to make a choice about where to go. So for example, you start here today, and you can go to A1 or A2. They're very romantically named. And this one's a distance of 8, and this is a distance of 3. And once you're, let's say, in the town of A1, then you can go to B1 or B2. And if you go to B1, it's a distance of 7. If you go to B2, it's a distance of 4. Okay? Similarly, if you happen to have chosen to go to A2 and you want to go to B1, well, that turns out to be very close, and B2 is a little bit farther at 3, and so on, and then you get to the very end. And so the question is, how do we choose the path? So every day we have some choices to make. How do we choose the path that gets us from here to here in the shortest distance? Okay? So this is pretty simple, and you could probably just stare at it and come up with the solution. But there's a systematic way of doing this kind of problem, and it goes by the name of dynamic programming. And it was first introduced by Richard Bellman in late 1950s. Okay. If you ever get a chance to read my book or look at it online or something, there's a nice story about how did it get this name, dynamic programming. Okay, so let's call a function j, which will turn into be rj, of x, is the cost to go. It's called the cost to go function. It means the cost to go to the end. And j star will be starting from x, the optimal or best optimal cost, let's say. Okay, so we can do this in a kind of systematic way. So let's say if we're at the end, then j star of the end is 0 because you're already there, so there's no cost. You don't have to go anywhere. If we happen to be, we're going to start at the end and we're going to kind of work our way back to the beginning. So we just consider this case. Now let's consider if we happen to start at B1, then what's the cost, the best cost? Well, it's just, there's only one way to go. So the cost is 3. So the j star of B1 is equal to 3. And similarly, j star of B2 is equal to 4. Okay? So again, if you're here, only one way to go. So this starts to get interesting when we look at the day before. So if we want to do j star of A1, now we have two choices. Okay? So we're here, if we're at A1, then we can either go to B1 and then to here, or we can go to B2 and then to here, right? So let me write, but we want the best cost, okay? So there's two choices, and we want to take the minimum of those two choices. So we'll say we want to take the minimum of the B1 route. So the B1 route would be 7 plus 3, okay? But let me write it in a suggestive way, plus j star of B1, okay, which is 3. So that's one possibility. The other possibility, you go 4 plus j star of B2. And then that minimum, which is the minimum? Let's just see if people are with me here? Sorry? 8. Okay, right, because it's let's see if it, yeah. So it's, right, so it's 4 plus 4, right? I'm sorry? So we're here. Okay, so we say 4 and then 4. So that would be 8. Or we can go 7 plus 3 is 10. So that's longer. So the minimum, so J star of A1 is 8. And we can do A2. So it should be, if I have my notes right here, 1 and 3 plus J star of B2, and that's equal to 4. Does this look right? Okay, because I'm just copying my notes here. So if it's silly, it's silly. Okay, so this is now J star of A1 and A2. So now here's the maybe non-intuitive part. That J star of A1. Okay, so my claim, and we'll try to justify in a moment, is that I can do exactly the same structure to find out the best cost. Okay, so what I claim is that I can say it's the minimum of, I have 2 possibilities. So it's whoops, did I? Start 2. Oh, I'm sorry. Okay, when you get to a certain age, numbers start to get a little unclear. I think this is supposed to be 2. Yeah, this is supposed to be a 2 here, sorry. A 2 and an 8 don't look all that different. Okay, so it's 2 plus J star of A1 and 3 plus J star of A2, and that's equal to 7 because this was J star of A1 this was 8 and this was 4, so 3 plus 4 is 7, and that's the minimum. Okay, so the step that's not obvious is that it was sufficient to write this, like 2 plus the best root. And the reason that this is the case comes from something that Bellman called principle of optimality, which is this sort of, if you have an optimal trajectory in this kind of problem, it's not like what you were talking about the other day, where, for example, if we start with a point here, then if this is the optimal trajectory to go from start to end, if we pick a point here, this is also on the optimal trajectory from here to the end is just this remaining part. Okay, and the reason is that everything here is just added in stages. That's sort of the key step that you don't have in general. And so you were talking about cases that don't have this, but in this particular set of journeys, everything that we do from, we go one day and we make a choice, one day and we make a choice, and one day and we make a choice. And so it's just sufficient to calculate. So what we're ending up doing is sort of calculating things going backwards. And all we have to do at each stage is look at what are the possibilities of now, and then have recorded previously what were the best routes from the particular city. Okay? J star. So this is the best route from A2, the lowest cost route from A2, which already had a choice to make. Okay, but at this stage, we don't have to revisit that choice. We can just use the best route and then use this idea that this path will decompose. Okay, so the fact that we have kind of a running cost, a day-by-day cost to pay, means that this problem has a, this sort of problem of repeatedly making decisions has a special structure. Okay. So I think if I only have a few minutes, let me just sort of, there's a lot more in the notes on step by step, but let me just sort of give you the flow of thought that comes. So the next step would be to go back to our general structure. I think I can. Cost here, so we have, so we'd be doing a discrete version at first of the problem we've been doing, where xk is the state at time k, uk would be the action that you take, the control that you take at time k, L of xk, uk, which we could call lk, would be the running cost of stage k. So stage is kind of like time, a discrete time. And then our j of the just evaluated in the local time could also be a jk, and that's again this is the cost to go. And so then we can write j as a sum from 0 to, let's say, n-1 of our lk, and if we had some final costs, we could also add in the final costs, which would be sorry, this is the final cost. Okay, so this is phi of xn, and so so this is a sum of a running cost plus a final cost, and we can decompose this into the lk for just one stage, plus the sum starting from n equals let's see. Sorry, this is, yeah, sorry, this, I'm sorry, here we're just starting from k here. Sorry, I'm just skipping too much steps. So I just skipped a step here. Sorry, let me define jk as the sum starting from the cost starting from time k of all of this L of xk, uk. And so then this is then we can write this as lk plus the sum starting from k plus 1 to n-1 of L and phi of xn. But this is just j k plus 1. Okay, so the structure of the cost function, because it's a sum over these running costs, means that the cost at time k can be expressed as the immediate cost at time k plus the cost from time k plus 1. Okay, and so then, but then we can imagine choosing u at each time to minimize the cost jk. And so, so if we choose, so then what we can show is that j star of x k is the minimum over all the possible uk that you could choose of L of xk uk plus j star of xk plus 1. So notice j star is only a function of where you start, because this means you've chosen the optimal u. So there's no more u in here because you've chosen the best, and that's reflected in the star. So this equation here is exactly what we were imposing here. Okay, but just now written for a more general cost function And so this is the discrete version of the Bellman equation. And so you solve this going backwards. The thing to note about it is that, so the structure would be, you solve this going backwards, just like you solve this here. Once you've solved it, at every stage going backwards, when you choose the minimum, then that corresponds to selecting a value of u, right? That's the action that you take. Here it was just, which city do I go to next? Well, wherever it went to. Which city do I go to next? In the general case, it would be what value of control u do I choose? And so, so you go through this recursion. At each step, you record the value of u that you would choose. And so at the end, when you finished this and gotten back to your initial condition, you also have a set of instructions of u, and then you can go forward in time solving x, k plus 1 is f of xk uk. And of course, again, I don't have time to go through it. This is done in discrete time, but you can now take a continuous time limit and come back with a continuous equation, which is called the Hamilton-Jacobi-Bellman equation. And as its name suggests, is the equivalent. Remember, in classical mechanics, you first do Newton's equation, Newtonian mechanics, then Lagrangian, then Hamiltonian. And if you survive that far, you do Hamilton-Jacobi. So there's, again, a Hamilton-Jacobi version of it. And that has some very beautiful properties to it. One of the things that I don't have time to talk about is that in the equations of motion, which, did they, no, okay, they vanish? Okay, so we had an equation, we had dx h 0, and then we had, lambda dot was minus, and then x dot was d lambda h. And then we had the equation du h equals 0. So one of the rather amazing theorems that was proved in the last century was by Pontryagin. He was a Soviet Soviet mathematician, and really one of the great mathematicians of the 20th century. Did all sorts of stuff in algebraic topology, cohomology, and very abstract stuff. But he also did some seminal work in optimal control. What he showed was that actually, if you have constraints on a problem, for example, let's say that you can only take a certain set of values, that there's a maximum value, or that the states can only go, the system is only allowed to go into a certain part of the state space, that you can replace this condition with just a minimization over an allowed set, for example, of h. So that you choose, u is the argument that minimizes so you choose the u that minimizes h. The reason that this allows you to deal with constraints is that, for example, let's say that h, if h of u look like this, you just take a derivative. But if h of u looks like this, and let's say u has to be between here and here, then you can minimize h, for example, by choosing this value of u. Okay, so if you have a constraint, the minimization may end up on the boundary of the constraint, even though there's no, and you still have a minimum, even though there's no derivative equal to 0. So it sounds maybe a little bit trivial to replace this condition, which comes out of the Euler-Lagrange equations, with this thing, but it's actually a very hard theorem to prove, and it was actually unexpected too. So when it really was an advance when he realized this. So this allows you to do all sorts of problems where there are constraints. For example, getting from A to B in minimum time, or taking into account for the fact that your control has a bounded value. So that would be one thing. But the example I wanted to end up on is, again, just in words. We solved earlier a problem like this where we went from x naught to xt, and the equations that we got, these Hamiltonian equations, what they give you in general, like for the pendulum, is not a feedback solution, but a feed-forward solution. That is to say, you get a u of t that comes out of it, but this is just a u dependent on time. It's not related to the state of the system there. And in the special case of linear dynamics, I showed that that was not true. That, remember, in linear dynamics, we had u was proportional to lambda, and lambda we used an ansatz like this that worked. And so u and x were related, and there was a natural relationship of the form that popped out. So in the case of a linear system, these equations do give rise to a feedback law, but in general, that's not true. But what you can do, and it's not, the best possible thing in all situations, is to solve for this feed-forward problem. So for example, this is the sets of torques that you have to do to take the pendulum from here to here. And so this will give you u of t equals some u feed-forward solution, and then allow for deviations. These deviations might be because there are external forces, perhaps stochastic forces affecting the trajectory. So this would blend in with stochastic thermodynamics results, which I'll talk about a little bit more tomorrow, or just kicks by somebody, or even, for example, your equations of motion are not correct, right? Maybe you have parameters that are incorrect for the length of the pendulum, or maybe there's friction that you didn't put in and things like that. So you can have deviations from, this, you have the u of t, and the u of t is supposed to generate an x of t that looks like this, but the real x of t might deviate. And if you're trying to get to an unstable point, that can be a very serious deviation. It means that it won't get there and it won't balance at the end. But what you can do is add in a feedback solution. And this you can calculate by basically starting off with just as some function of time and just assuming that this is small compared to this, and just doing a linear expansion of everything in sight, including the cost function. So you have some cost function L, which doesn't have to be quadratic, but you've solved for the trajectory that gives you, in principle, where delta J is equal to 0, if we go back to the Lagrange version that we did at the beginning. And so you can, if you have deviations to first order, they won't change the cost, but to second order, they'll increase the cost. And so you can expand and show that you actually get like a quadratic form. And so you get something that is of the form, an integral over time from 0 to t of something like xt q of t x plus ut r of t u. And the only difference is that these are time-dependent functions, because you're expanding this cost function in different, it's not itself quadratic, but it has some minimum, and then you locally expand it depending on where the system is. And then once you do that, you can also linearize the equations of motion about this trajectory. And you get something of the form that we've been studying, except now the matrices A, B, and C, and D are all time-dependent. And then you can go back and do the linear solution that I talked about, which, by the way, is called linear quadratic regulator, LQR. So it's linear equations of motion, quadratic cost function, and trying to make x equal 0. But now the x is the deviation not from a fixed point, but from a trajectory. So everything has the same structure as what we talked about and just did the exact solution of, except that everything is time dependent. All the Q, the R, the A, the B, the C, and so on are all time dependent. But it turns out that doesn't matter. Everything that we did in the solution continues to hold with just time dependent terms. And also, I guess, actually, you get this, but you also get a cross-coupling term in general, so you'll get something xtu here as well, and a symmetric version of it. This gives a nice, relatively general way of controlling a nonlinear system, which is that you first solve for the feed forward, doing the stuff that we did at the beginning of the hour, and then you allow for a linear feedback around that, that will take care of at least small deviations. And to be even more robust against big deviations, you can periodically recompute the situation. Like if you ever get a big enough perturbation, then you can just sort of say, okay, all hope is lost, but I know where the system is, so let me just start the whole problem all over again. This is like what happens if you're driving in a car and you have GPS and it's telling you how to get to your destination, and you make a silly wrong turn. It just says recalculating, and then it tells you the new directions. So you can do that. So if you put all of that together, that's a pretty general and robust way of controlling just about anything. So I'll stop there. So tomorrow, everything I've done here is deterministic. So we want to put in stochastic perturbations and so forth, and measurement noise, and sort of see what happens then. And then that'll make closer contact with the stochastic thermodynamics and things. Okay. So again, I apologize for the exponential speed up at the end. There you go.
We can maybe find a partial differential equation for the J star. I don't know, similar to Hamilton-Jacobi equation or something like that.
So this equation here can be generalized to a partial differential equation. Yeah, this is the Hamilton-Jacobi Bellman equation, it's called.
Okay. Yeah, it's because the formalism is similar to the classical dynamics.
Yeah,
so that's...
yeah. So again, if you liked advanced classical mechanics and Hamilton-Jacobi, this is really very much in parallel with it. And if you're an experimentalist like me who is always dodgy on it, then it's still a challenge, but yeah.
Okay, thank you.
Typically, you want to optimize in time. You want to make things as fast as possible. But I did not see you optimizing tau.
Right. So I did just in words. In formulating this cost function, yeah. Everything that I did on the board was assuming that tau was fixed. Yeah. But you can make tau a variable as well, and then when you take your variation, you also have to allow for variations in tau. So then you can write it down. But this won't make any sense in linear systems because you can always make things arbitrarily fast by using arbitrarily large inputs. So where sort of that kind of optimal control is typically encountered is when you combine this with a constraint, for example, on how large a U that you want to do. So for example, the classic simple problem, which is in the notes and I didn't have time to get to, is you have a car and you have let's say there's no friction, but you have an accelerator, maybe it's a rocket, and you want to get from A to B, from here stationary to here stationary in minimum time. And so the solution then would be accelerate to the maximum amount possible to about halfway, and then brake as much as possible to the long. So that's called bang-bang control. Part of the reason that I didn't get to, I didn't get to it because of time, but part of the reason I put it in the things that I didn't get to explicitly is if you think about the car example, this isn't a very safe way to get from A to B, right? And so it lacks a certain robustness. Like you're going and you're braking as much as you can, and then a kid runs out in front of you, you can't brake any harder because you're already braking as hard as you can. So I would actually argue that if you're at all concerned with robustness, then the kind of thing that I was talking about where you compute something without constraints, but just choosing penalties so that you don't have too, the time of the protocol, so that you don't have too large an amplitude of control required, and then allowing for corrections about it is a much safer way to go.
Yesterday you mentioned that there is a geometric way to look at all of this with Lie brackets and stuff like that. When one does that type of geometric formulation, can you gain more insight, or is it just a fancier way to put the theory?
Well, okay, I'm probably not the person to ask for it because it gets fairly abstract. To be honest, all the results that I've seen basically amount to kind of fancier ways to calculate things that you could do in other ways.
Okay.
I mean, there's some cute results that come out of it. For example, like one of the classic results that comes out of that kind of thing is showing that you can park a car in a space that is epsilon longer than the car if you're willing to make enough maneuvers. That you can always, even though your control is only sort of back and forth and steering, that the combination of those can make you go in different directions. And that's something you can show with Lie brackets. But this, again, I think it's sort of fancy ways of doing things that you could probably do in other ways too.
Thank you.
In the example of the pendulum, you go from the stable position to the unstable, and I suppose if you don't control anymore, it will fall. Is there a way to keep it there, or at least
I'm sorry?
to keep it in the
Yeah.
unstable?
So once it's either at or near the maximum, then then essentially you can the feed forward control is 0. So and then you just use the linear quadratic regulator to so this LQR. It doesn't, nothing I said depended on whether the system was stable or unstable. So you can design a control, and basically it amounts to deriving the k in the u equals minus kx. So you have here in this case it would be a two-dimensional system, so to have two components, and you would be deriving. I mean, that's such a simple example and you can also do this with proportional feedback and derivative feedback, so proportional and velocity feedback. So you could just think of it, again, just like my very simple example, that this fancy way of saying is just choosing a proportional gain and a velocity gain to stabilize.
Okay, thank you. So we have a coffee break of 20 minutes.
Okay.
This minimization of the power
Yeah.
isn't this similar? There is a thing called Dijkstra algorithm, something like that.